Imagine hiring a world-class chef, right? And they prep this meticulous 7-course meal for you. But halfway through, they plate a completely raw onion, tell you dessert has already been served, and then, like, completely forget why they are even in your kitchen to begin with.
It's a terrifying thought.
Right. It sounds absurd, but I mean, if you've ever tried to get an autonomous AI agent to complete a complex, multi-step task, you've probably watched it fail in exactly that bizarre, frustrating way.
Yeah, absolutely.
You give it a goal, you provide some software tools, and somehow it just wanders off into the weeds, hallucinating steps, abandoning its original plan. Today, we are exploring exactly why that happens, and more importantly, how a radical new solution is fixing it. Welcome to the Deep Dive.
And, today's mission is a critical one for you, the listener, especially if you are navigating the rapidly changing world of artificial intelligence. We are examining the state-of-the-art in generative AI, really focusing on foundational research here.
Always the best place to start.
Exactly. Our entire discussion today is grounded in a 2026 paper titled LLM-as-Code, Agentic Programming for Agent Harness. And this was written by researchers from the City University of Hong Kong and Tencent Jarvis Lab.
Okay, let's unpack this, because the researchers are calling out a massive fundamental architectural flaw in how AI agents are currently being built. So what is the status quo right now? Like, how are we building these AI agents that are failing so spectacularly on long tasks?
Well, currently, almost every major AI agent framework, so think of popular systems like AutoGen or OpenHands, MetaGPT, they all use a model heavily influenced by something called React.
That's React as in reason and act, right?
Yes, reason and act. It's essentially a loop where large language model, the LLM itself, is placed squarely in the role of the orchestrator.
The boss.
Right, the boss. You give the AI a prompt and it generates a thought about what to do. It takes an action by selecting a tool, waits for the observation from that tool, and then generates another thought.
So the AI is literally sitting in the manager's chair. It alone is deciding, when to loop, what tool to pull next, when to declare the job finished. And I mean, on short, simple demonstrations, that looks incredible.
Oh, it looks like magic.
Yeah. A single text prompt replaces pages and pages of complex orchestration code.
It feels revolutionary right up until you ask it to do something that actually takes a long time. Like, say, a massive multi-file software refactor.
That's where the wheels fall off.
Completely. The researchers point out that when you give the LLM as orchestrator a long horizon task, it reliably breaks down. And it breaks down because a text generation loop is essentially masquerading as a control loop,
I see, sir.
which leads to 3 very distinct symptoms of failure. First is what they call token explosion.
Token explosion. Okay, what's that?
Well, because the LLM needs to know where it is in a multi-step process, it has to constantly reread the entire history of everything it just did.
Like constantly rereading its own diary just to know what day it is.
Exactly. And as that transcript grows endlessly longer, the AI's attention mechanism gets stretched way too thin. It literally forgets its original root cause hypothesis.
So it suffers from a kind of amnesia because it's just drowning in its own notes?
Precisely. And that leads directly into the second symptom, which is control flow hallucination.
That sounds like a sci-fi term.
It does, but it's very real.
Mm-hmm.
When the AI loses track of the actual procedural reality, it starts generating text that merely sounds like the correct next step.
Okay, so it's just making things up that sound plausible.
Right. It will confidently report that a critical bug is fully fixed and just move on before it has even bothered to run the verification test to prove it.
Plating the raw onion and calling it dessert. It hallucinates that the procedural step actually happened just because the text prediction favored those specific words.
You nailed it. And the third symptom is unreliable completion. Let's say the AI formulates a flawless multi-step plan, right? Halfway through execution, a minor, completely unrelated error occurs. Because the LLM is orchestrating everything dynamically, it often gets completely swayed by this new error. It abandons the correct overarching plan entirely and just spirals down a rabbit hole trying to fix a symptom rather than the disease.
Man. I was trying to think of an analogy for this kind of brilliant but totally erratic behavior.
Let's hear it.
It's like hiring a highly creative abstract painter to do your taxes and manage your daily schedule.
Oh, that's good.
Right, because they are undeniably intelligent and they might write you a beautiful, insightful summary of your financial philosophy, but they will absolutely forget to put the actual tax forms in the mail, they simply aren't built for rigid, step-by-step compliance.
What's fascinating here is that the authors of the paper argue this exact point. They state that these failures, so the token explosion, the hallucinations, the unreliability, they're not temporary bugs that will magically disappear when we get the next generation of models.
Really? Because you always hear, oh, GPT-5 or 6 will fix that.
Exactly, but the researchers say no. They argue these are architectural consequences of a fundamental category error.
A category error. Explain what they mean by that.
Well, we have to look at the underlying mechanics of these systems. An LLM is, at its core, a probabilistic system. Its entire architecture is designed to predict the next most likely token or word based on statistical distributions.
Right. It's an incredibly advanced guessing machine.
Yes. And that makes it incredible at tasks where the correct answer requires reasoning under uncertainty, like summarizing text or generating ideas. But we are taking this probabilistic engine and demanding that it do deterministic work.
Deterministic meaning actions that must happen exactly the same way every time without fail.
Exactly.
Things like executing a loop a specific number of times or following a really strict if-then branch.
Let's examine a specific example the researchers use in the paper to illustrate this. Imagine a very simple task. You want an AI agent to fetch exactly 8 URLs, summarize the content of each one, and then compile a final report.
I mean, that sounds like a trivial task for an advanced AI.
You would assume so. But under the LLM-as-orchestrator model, the AI is relying on probability to run that loop. So it fetches URL 1, summarizes it. It fetches URL 2, summarizes it.
Okay, so far so good.
But by the time it reaches step 4, the probability distribution might just happen to favor the tokens for URL 1 again.
Oh, wow.
So it refetches URL 1, duplicating its work. Then it might completely skip URL 5. And by step 8, the statistical weighting might just lead it to output, I think I'm done, here's the report, completely missing the fact that the actual looping mechanism was never completed.
That is wild. And it's because it isn't actually running a loop, is it?
No, it's not.
It is just mimicking the syntax and appearance of a loop in a text sequence, because if you asked a traditional programming language like Python to run a for loop 8 times, it guarantees exactly 8 iterations.
Exactly.
No skipped steps, no repeated steps, no early stops. The language runtime enforces it mathematically at the processor level. So by asking an LLM to manage that loop, we are essentially throwing away decades of reliable computer science just because the AI is really good at chatting.
That's the crux of it. If the core issue is that LLMs are probabilistically guessing their way through deterministic tasks, we have to look at how the industry has tried to solve this so far.
Right, the Band-Aid fixes.
Yeah, the communities has attempted a rich line of patches, but the paper argues they're treating the symptoms rather than the underlying disease. Take the massive push for larger context windows. We now have models that can hold millions of tokens in their memory at once.
Which seems great. Shouldn't a massive memory solve the token explosion problem? If it can remember everything, it shouldn't get lost, right?
It just delays the inevitable. The underlying mechanism of an LLM requires it to calculate the relationship between every single token in its context window. So when you feed it a massive, flat, continuously growing transcript of a complex task, you run into the needle in a haystack problem. The attention mechanism gets diluted.
So the AI's reasoning actively degrades.
Yes, and often long before you hit the hard limit of the memory window, it starts ignoring constraints you established 20 steps ago. Furthermore, computing all those tokens becomes significantly slower and exponentially more expensive. A giant flat log is fundamentally the wrong data structure for managing complex, branching tasks.
Well, what about self-reflection? I see this approach all the time where developers write system prompts explicitly instructing the AI to, double check its work or retry if it encounters an error. Does that self-correction loop help?
Self-reflection does lower the error rate on any single isolated step, but we have to consider how probabilities compound over time. The decision to retry and the critical decision of what exactly to retry is still being sampled probabilistically by the LLM.
So you're saying the retry mechanism itself is flawed?
Right. You haven't eliminated the error. You've just slightly reduced its likelihood on a per-step basis. If an agent has a 95% success rate per step, and it takes 50 steps to complete a task,
the math is going to catch up with you.
Exactly. The math dictates that the whole task will almost certainly derail before the end.
Let me push back on this a bit, though. If the issue is the AI wandering off or skipping steps, why can't I just give it a very strict, highly detailed checklist right in its system prompt? Like, if I explicitly write, "Thou shalt not skip these steps, and you must do X before Y," Want a sufficiently smart model, simply follow the instructions.
You'd hope so, but the empirical data proves otherwise. The researchers tested this exact hypothesis using a software engineering task that involved about 20 specific rules.
20 roles, like what?
These included naming conventions, requiring type-ins, and crucial procedural rules like run the linter before any code commit.
So a mix of stylistic preferences and absolute must-do actions.
Yes, a highly strict prompt. But empirically, the AI simply cannot hold all of those constraints in its active attention simultaneously as the task progresses. By step 5, it predictably starts forgetting the procedural rules entirely.
By step 5.
Yeah. What happens under the hood is that all these rules start competing for the AI's attention. How does an LLM resolve conflicts when multiple rules apply? It doesn't use strict precedents. It relies on token sampling.
Meaning it relies on temperature and probability weights.
Yes. It assigns percentage weights to different words, and if two rules conflict, it essentially spins a roulette wheel to decide which rule to follow next. You can coach an LLM toward compliance through prompting, but as long as it operates as the orchestrator, you can never mathematically guarantee it.
Okay, here's where it gets really interesting. Because the researchers aren't just cataloging these failures, are they? They are proposing a radical solution, and they call it agentic programming.
Yes. This is the core paradigm shift of the paper. The fix requires a complete role reversal. We literally strip the LLM of its management title. It is no longer the orchestrator.
We are demoting the AI from project manager down to a specialist.
Exactly. Or rather, we are placing it in the exact role its architecture was actually designed for. In agentic programming, the program itself, the ordinary deterministic code written in a language like Python, controls the entire workflow.
So the code is the boss now.
Right. The LLM becomes a subcomponent, just a function called within the code, and it is only invoked when fluid reasoning or generation is genuinely needed.
So instead of the AI running the loop and deciding when to fetch a URL, the Python code runs a strict mathematical for loop. Inside that loop, the code fetches the data and then calls the LLM saying, hey, summarize this text.
Precisely.
And then the LLM does what it's uniquely great at, summarizing, hands the text back, and goes dormant while the deterministic code handles the next step.
It is a purely code-driven workflow. The operational rules are no longer begged from the model in a lengthy, hopeful prompt. They are executed by the runtime environment. If your workflow requires that a security check must run before a file is written, the Python code guarantees it runs.
The AI isn't asked to remember the rule.
No, the AI doesn't even possess the power to bypass the rule.
You know, if you are listening to this and you manage projects or build software tools, think about it like this. The old way, the orchestrator model, is like handing an employee a flowchart and just hoping they follow it step by step without getting distracted.
Right.
But this new approach, LLM-as-Code, is like physically building a roller coaster track. The AI gets in the cart and it literally cannot fall off the track. The steel rails dictate exactly where it goes, and it only has to do its specific job at the designated stations along the way.
That is a highly accurate way to visualize it. The fluid flexibility of the LLM is preserved entirely at the node level, where reasoning is needed, but the reliability of the overall system is anchored in the deterministic track.
That clearly solves the hallucination and unreliability problems, right? The track won't let it wander. But how does this new setup fix the dreaded memory crisis? Because whether the AI is managing the loop or the Python code is managing the loop, a massive multi-step task is still going to generate a mountain of data. Doesn't the AI still suffer from token explosion?
It would if we still fed it a flat transcript. But the structure of how that data is stored and presented to the LLM changes completely in agentic programming. The context isn't a flat, endless conversation log anymore. It's structured computationally as a directed acyclic graph, or a DAG.
Directed acyclic graph. Okay, break down how that works in this context.
Think of it as a family tree of function calls, very similar to how traditional software manages a call stack. Let's visualize a simple chain of events. Call A starts the process. It triggers call B.
Okay, A to B.
Call B encounters a complex problem and needs the AI to do some reasoning, so it triggers call C.
So A branches to B and B branches to C.
Right. Now, while call C is actively running and the AI is processing its thoughts, the AI is only allowed to see its direct ancestor chain, A, B, and C. That narrow scope is its entire context window.
Keeping it focused.
Exactly. Now, let's say call C finishes its reasoning process. Under the old orchestrator system, call C's entire messy scratch pad, all its internal debate and intermediate steps, would just get appended to the forever growing log.
Like accidentally CCing the entire company on a massive disorganized email thread. Everyone has to read everything.
Yes. But with a DAG context structure, when call C finishes, its memory frame is released. The system collapses all of that messy intermediate work into a single, clean, one-line summary. Just the final actionable answer.
It's brilliant.
So when the program moves on to the next step, let's call it call D. Call D doesn't see C's 5 pages of rough drafts. It just sees the ancestors A and B, plus that neat little summary from C.
It's like having an incredibly efficient executive assistant. Call C does all the grueling research, but only hands Call D a single post-it note with the final number. Call D can focus entirely on its own task without being distracted by the history of how that number was calculated.
And the immense computational benefit here is that the context length is now bounded by the depth of the call tree, not by the total number of steps taken in the entire task.
So even if the agent takes 1,000 steps to finish a complex job, the AI at step 1,000 isn't burdened with processing the transcripts of the previous 999 steps.
Exactly.
It stays sharp, focused, and I have to assume dramatically cheaper to run because you aren't paying for millions of tokens every time it breathes.
It completely relieves both the hard limit of context windows and the soft degradation of reasoning quality. The AI is always operating in a pristine, highly relevant context.
Okay, the theory makes total logical sense, but we have to demand the proof. We've seen countless theoretical frameworks that look elegant on paper but just fall apart when applied to real software.
Sure.
Does putting the LLM inside a rigid code harness actually perform better in the wild?
Well, the researchers put this framework to the test using the AWS World Benchmark, which, if you don't know, is a highly rigorous test for GUI automation, basically getting an AI to actually operate a computer interface, click buttons, and navigate menus to achieve a goal.
Okay, so a real-world stress test. Let's hear the hard numbers.
On the standard AWS World Benchmark, the very best mainstream agents, those using the React orchestrator model, they maxed out at an 80.4% success rate.
Okay, 80%, not terrible.
Right, but to achieve that 80.4%, they had to burn through their maximum allotted 100 steps.
Oh, wow.
They were continuously looping, hallucinating, failing, and retrying until they practically hit the wall.
80.4% success, but taking the absolute maximum 100 steps to get there. How did the LLM-as-Code agent perform?
The LLM-as-Code agent hit an 86.8% success rate.
That is a significant jump in accuracy for a benchmark that notoriously difficult.
But the success rate isn't even the most impressive part. It didn't take 100 steps. It achieved that 86.8% success rate in just 15 steps.
15 steps.
15 steps.
It is dramatically more accurate and almost 7 times more efficient. Because it isn't wasting time in compute cycles convincing itself to stay on track, the track is doing the heavy lifting.
Exactly. And this efficiency becomes even more powerful when you apply the framework to multi-agent collaboration.
How so?
Well, this structure allows multiple agents to work together flawlessly because they are deployed as parallel functions in the code, rather than conversationalists in a chat room.
Give me a tangible example of how that multi-agent collaboration works in practice.
Let's use software code review as an example. In an orchestrator model, if you want 5 agents to review 5 different files, you usually have them operating in one shared chat window.
Sounds like a nightmare.
It is chaos. The context gets tangled, they interrupt each other, and they hallucinate based on each other's code. But with agentic programming, a parent agent simply executes a code loop that dispatches a separate subagent for every modified file.
So 5 files modified means 5 parallel subagents automatically spin up.
Right. And because they are just isolated functions in a DAG, they don't share a massive, confusing context window. Subagent 1 only sees file 1. Subagent 2 only sees file 2.
That is so clean.
They do the specific reasoning, and when they finish, their frames collapse, and they return clean summaries to the parent agent. The parent agent then joins those summaries using deterministic program logic, like mathematically deduplicating findings or sorting them by severity rather than asking another probabilistic LLM to guess how to merge them.
It is an incredibly clean architecture, but this raises a major question for me. If we are locking the AI into this strict, hard-coded track, how does it ever learn? How does it evolve? Doesn't this completely kill the dream of a self-improving AI? I mean, if the track is rigid steel, the cart can't invent a better track, right?
That is a very common concern when developers first look at this paradigm, but the authors address it beautifully through a mechanism they call self-programmed evolution.
Okay, tell me about that.
The AI absolutely can propose new agentic functions. A meta agent can observe a failing workflow, realize a new tool is needed, and write new Python code to handle it.
But wait, if the AI is writing new code probabilistically, doesn't that just introduce the exact unreliability we just spent this whole time trying to eliminate?
It would, except for how that new code is accepted into the system. The LLM proposes the new function probabilistically, yes. But before that new function is allowed to become part of the actual workflow, it must pass the program's strict deterministic unit tests.
Ah, so the AI is allowed to suggest a new idea, but the traditional software environment acts as a ruthless bouncer.
Exactly.
If the code doesn't compile or if it fails mathematical tests, it just gets rejected at the door.
And if it passes those deterministic tests, it is saved as permanent, durable code. The system evolves by writing hard rules into its own architecture, not by trying to hold on to a lesson learned in a text prompt and hoping it remembers to apply it next time. It hardens its own track.
So, what does this all mean? If we step back and synthesize everything we've explored today, the core takeaway is really about the true nature of reliability.
I agree.
If you want a system to be reliable, you absolutely cannot delegate deterministic control. The loops, the verification checks, the exact sequencing to a probabilistic engine that operates by statistically guessing the next word. The future of autonomous AI isn't about giving the AI more freedom to manage itself. It's actually about stripping away that freedom and putting it inside a strictly coded harness.
And if we connect this to the bigger picture, it really is a return to fundamental computer science principles.
Right.
Programming languages have spent the last several decades perfecting control flow. We have bulletproof ways to run loops, manage memory, handle exceptions. We shouldn't throw all that away just because large language models happen to be incredibly impressive at reasoning. We need to marry the two, leveraging the flawless control flow of traditional code to drive the adaptive reasoning of the LLM.
It's about letting each tool do exactly what it was mathematically designed to do best.
That is the essence of LLM-as-Code.
As we wrap up today's deep dive, I want to leave you, the listener, with a provocative thought to ponder on your own. If the absolute most reliable way to use artificial intelligence is to intentionally strip it of its autonomy, to box it into rigid software functions where it cannot make its own plans or deviate from a pre-written track, what does that mean for the grand pursuit of fully autonomous AI that the tech industry is so obsessed with?
That's a great question.
Are we truly on a path to building independent digital workers who can think, plan, and act entirely on their own? Or are we really just creating highly advanced probabilistic calculators that ultimately must be strapped to the engine of traditional software to get anything useful done? Next time you hear someone hype up a fully autonomous AI agent that is going to manage your entire life, just remember the chef. If you don't build a track for them, you might just end up eating a raw onion. Thanks for joining us on this deep dive.